Hi, Rockstars. Today we will be advancing in our physics ignition series and we will be taking the topic thermal energy, heat energy, expansion of solids. In the class today we will be splitting the class into 5 different sections. In the first section we will be talking about the concept of heat and temperature, where we will be defining this concept, talking about the differences between these two concepts. We will talk about the effect of heat and how the kinetic theory of matter explains temperature and heat. Secondly, we will be talking about the expansion of solids, under which we will talk about the effect of expansion, the application of expansion, and even ball ring experiments. Thirdly, we will be talking about heat transfer, the conduction, convection, and radiation, and the application in thermoflask. Fourthly, we will be talking about the calculatory aspect of expansivity. And lastly, we will be using this knowledge to crush UTME questions. Stay with me. Greetings, future rockstars, and welcome to Josh White Academy, where we fuel your success with experience-backed strategies and science-based tutorials. If you are new to this channel, I am your host, Josh White, and it's my mission to help you crush high school with confidence and clarity. So please do well to smash that subscribe button, turn on the notification. Let's get started. The concept of heat and temperature. You see, these two phenomenon are many times confused by high school students. Now see, heat is actually a form of energy that is transferred from one part to another due to temperature difference. Whereas temperature is just a degree of how hot or how cold a body is. So we define temperature as the degree of hotness or coldness of a body. Now you see, heat can be produced via different sources. For instance, the heat from the sun, solar heat. The heat by rubbing two surfaces together, like your palm, by friction. That's the heat by friction. Or the heat even through chemical reactions, like for instance introducing sulfuric acid, that's tetraoxosulfuric acid, into water. So all of these can produce heat, and heat can be used for different things, like in laundering purposes, like in ironing our clothes. Heat can be used for cooking. Heat from coal can be used to power trains. So you see, heat is actually a form of energy. Now, to differentiate between temperature and heat, number one, heat is a form of energy, whereas temperature is not a form of energy. Temperature can be measured using an instrument called thermometer, and there are different types. Whereas heat can be measured, like heat capacity can be measured using our calorimeter. Temperature is measured in Kelvin, but there are other units for measuring temperature, like Celsius, degree Celsius, degree Fahrenheit, or degree centigrade, Rankine, Newton. But the SI unit for temperature is Kelvin. Whereas heat, because heat is a form of energy, heat is measured in joules, because it's a form of energy. Number 4, we said temperature is a degree of how hot or cold a body is. But heat has to do with a transfer due to temperature difference. It's a form of energy that is transferred based on the differences in temperature. These and many others are the differences between temperature and heat. So please take note, they are not the same thing. Now, remember the kinetic theory of matter explains that matter are made up of tiny particles called atoms or molecules. And it has been explained that these molecules are in constant motion. That means they bear kinetic energy. And experiments have shown that increase in the temperature of a body culminates to an increase in the movement of these particles. That means if a body receives an increase in temperature due to the application of heat, the molecules, the atoms forming that object or substance moves faster. That means the degree of randomness or entropy increases. So in simple statement, temperature increases the average kinetic energy. Temperature is directly proportional to the average kinetic energy, whereas heat controls the general energy of that body. So, effect of heat. Now, when heat is applied to a body, it can cause different things, ranging from physical changes like shape, like color, even chemical changes can be altered due to it. Heat also causes change of state, like me applying heat to an ice block. It begins to melt from a solid state to a liquid state, and if I continually subject that body to heat, it changes from liquid to gaseous state. So that means heat causes change of state. Also, heat can cause thermionic emission, which is a phenomenon where a metal emits electron when heat is applied to it. But my main concern about the effect of heat is that heat also causes expansion of solids. And this brings us to the next section of the class. Let's talk about the expansion of solids. Solids expand when heated and contract when cooled. The rate of expansion of different solids differs based on the material of their making. For instance, the rate at which brass expands is higher than that of iron, steel, and invar. So, it is based on the material of that solid that determines how a solid expands when heat is applied or contracts when it is cooled. Now, let's explain the expansion of solids by using a ball and ring experiment. To appreciate the explanation of expansion of a solid, a ball is used, a metal ball, and it is observed that, let's say this is the ring and this is the ball. At the beginning, this metal ball can easily pass through this ring. Then heat is then being applied, and we know we will expect that body to expand. Now, and the ball can no longer pass through the ring because of what? Expansion has happened. And now, when this ball is allowed to then cool, it returns back to its original size, it contracts, and is now being able to pass through the ring. This proves that the application of heat causes that body to expand. And when the heat is removed, the body returns to its original shape by contraction. Now let's talk about the effect of expansion. Regarding the effect of expansion, we see it in railway lines and bridge. We also see it in buildings. And thirdly, we see this also in wires, like telegraph wires. Now, in railway lines and bridges, railways are always made in such a way that there are intermittent space between two parts to give space for expansion, because during the day where the sun is out, heat from the sun causes the metal to expand, and the railway and bridge are made in such a way that one part is fixed. Let's say, for instance, this is one part, and this is another part. This part is placed in rollers, whereas this part is fixed, so that when the heat from the sun will cause the body to expand, if these two parts are fixed and the body desires to expand, but there is no possibility of it expanding, the metal will begin to bend and break, destroying that railway. So what they do is, there are rollers here, so that when this body begins to expand, it can allow this metal to shift a little, thereby possibly covering more of this space. But if there is no space in between and the body wants to expand, it causes a breakage of that railway line. So always, railway lines and bridges are always giving space so that it can give space for expansion. And when it becomes night, where the stars begins to shine and the moon takes control and the sun is no more, the metal begins to contract back and return to its original size. Same with a building. You will notice during sunny day, you begin to hear some creaking sounds like this, because the galvanized iron used for roofing are expanding, and during the night you will see it, you will be hearing that same sound because it is now what contracting back to its original form. In telegraph wires, the metal used for making these wires in hot day, they expand and then sag. And when the weather becomes cool, they contract back. So the wires are made in such a way to give allowance. That means they are extra to give allowance for expansion. So these are some of the effects of expansion. Railway lines and bridges, buildings and telegraph wires. All of these, they are made in such a way to avoid their destruction. When the metals or the expandable parts of the materials begin to expand in sunny time and contract when it is cooled. Now let's talk about the application of expansion. The knowledge of expansion has made producers to make certain materials to be able to give chance for this expansion using that knowledge that metal expands or solids expands when heated. Now it is then used for good purposes. For instance, the stopper of bottles. The stopper of bottles can be easily removed when you place the bottle into a hot water that is possibly boiling, but don't allow the stopper to also be in contact with it. So what begins to happen to this bottle, even though bottle is not a very good conductor of heat, the bottle begins to expand, and as it expands without the cork expanding, what then happens? It then becomes loosened and it is then easily to be removed. So as the bottle begins to expand, even the space here also expands, but the cork, which is most times either plastic, rubber, or even wood, which are very poor conductor, bad conductor of heat, they remain just the way they are. So the expansion gives way to easily remove stoppers of bottles. So that's one of the applications. We already knowing that solids expand when heating. Now we are using it for good. Another very important application of expansion is in the bimetallic strip. Now, bimetallic strip, as the name implies, bimetallic. That means there are two metals that are riveted together. That means they are joined together. And most times they use two different metals whose rate of expansion differs. A classical example is between brass and iron. Brass expands more than iron. Let's say, for instance, these are our bimetallic strip, where here is our iron and here is our brass. We will notice when heat is applied to this body, it will look something like this, a shape like this. Yes. Because you know that brass expands more than iron. So the brass curves with it being outside. This is our brass outside with our iron, which has a lesser rate of expansion, is inside. So now this bimetallic strip is used in our laundry iron, is used in our water boilers, is used in a refrigerator. It's also used in bimetallic strip thermometer. And the idea is similar. Like for the laundering iron, what happens is, to be able to control the temperature or the heat from the pressing iron, when the light or when the electricity is turned on and the metallic strip begins to heat up, the brass then begins to bend. You know, when the iron is on, it is just similar like this, and the contact point is here. So it joins together, so electricity continues flowing, converted to heat. And as the heat of the iron begins to increase, you know, a temperature will be reached when brass will begin to expand, and it will begin to bend like this. So there will be a separation of the contact point, and then the iron will turn off. If you remember some scenarios where you were just ironing your clothes, and when the iron becomes very hot, you see the light in it will just turn off, and after some time it will turn on again. What happens simply is the bimetallic strip, when the iron is on, is in contact with this point, which means it's allowing electricity to pass through, which is then converted to heat. So as the temperature begins to rise, the brass will now expand, thereby bending, taking itself away from the contact point. So it will switch off the circuit. So current will no longer be flowing. So the temperature will begin to drop. And as the temperature begins to drop, the brass will now start contracting again. It will contract to return it to its original size, coming back to this contact point. So that cycle continues, turning on and turning off the electric iron or boiling water or water boiler. Now, it is similar in the case of bimetallic strip thermometer, where two metals are used, brass and steel or invar. Steel and invar have a far lower rate of expansion as compared to that of brass. So the bimetallic strip is just like something like this, where it is coiled round, a point of it is fixed and the other is connected to the pointer. So as the heat is increased, the brass begins to turn, making the pointer to read on a calibration, thereby measuring the temperature of that body. So that is what classically the knowledge of expansion is used in our laundering irons, boilers, refrigerators, and even the bimetallic strip thermometer. Now let's advance to the third section of this class today. Let's talk about heat transfer. So remember, we explained at the outset of the class today that heat is a form of energy that is transferred from the hotter body to a colder body, or from one part to another due to a temperature difference. That means heat can be transferred. Now, there are three major forms of heat transfer. There are three types of heat transfer. Number one, we have conduction. Number two, we have convection. And number three, we have radiation. Now, conduction simply means the transfer or movement of heat in a metal surface from the hotter part to the colder part, similar to the definition of diffusion. Is the movement of molecule of a substance from a region of higher concentration to the region of lower concentration. In the case of conduction, it's also the movement of heat from the region of high concentration or from the region of high temperature to the region of low temperature without the actual movement of the heating part. That means, for instance, let's take a rod, and this part of the rod is heated. You will notice that this body does not even need to move. After few minutes, this other part will begin to feel hot. How that happens is via conduction. You can try this at home by, if your cooking utensil is completely metal, put it inside a boiling food. You will notice that after the handle starts becoming hot, and that's the reason why our cooking utensils, the handle is made up of plastic, rubber, or even wood, because these are poor conductor of heat. So even though the metal part is getting hot, the handle still is not hot because they are bad conductor of heat. Now, convection is actually the movement of heat in fluid. You must take note. What happens with fluid? Fluid can be gases, that's air, or liquid. Due to the actual movement of the heated part. So, for instance, if this is most times, convection is most times seen in air conditioning. We know that heated air expands and then becomes lighter because it does not increase in mass. So, what happens in an air conditioning room is the heated air are less dense, so they go up, whereas the cool air, which is more denser, comes down. In that way, continual influx of the cooled air from the air condition displaces the warm air, making the room to become cool. Also, the heating of the room by wood fire, as seen in polar regions like Russia, in the European countries, in America, where there is a particular place where there is wood fire, and the whole room tends to become warmed. It's by convection. Because the heated part of the air then flows. That is heat transfer by convection. Imagine I taking a spoon of hot tea. What do we usually do before we eat them? or we want to eat food that is hot, we blow air on it. What we are doing unconsciously is we are chasing the warm air with our cold air. Remember, cold air is denser than warm air. So by doing that, the warm air leaves being replaced by the cold air, making the food colder. So that's heat transfer by convection. Another natural application of convection is in the land and sea breeze. During hot time and in summer, the land becomes hot because of the heat of the sun, whereas the water in the day still remains cold, which is reversed in the night, where the land becomes cool and water becomes warm. So land breeze and sea breeze, this is convection. And lastly, we have radiation. Radiation has to do with the movement or transfer of heat without the need of a material medium. For instance, the way the heat of the sun reaches us is through radiation, because the intervening medium is not heated. So radiation is a type of heat transfer where heat moves from one part to another part without hitting the medium. So radiation can take place even in a vacuum. So these are the three types of heat transfer. Heat transfer by conduction from one heated part to another part without the movement of the heated part. Convection, there is movement, and it has to do with fluid, air, gases and liquid, whereas radiation just has to do with the flow without need of a material medium. Dark bodies are good absorber of heat and bad reflector. So, and that's the reason why if you wear a black cloth, a dark colored cloth in the sun, in a sunny day, you sweat profusely, because black clothes are good absorber, good radiator of heat and bad reflector. Whereas white colored clothes or silver colored clothes or clothes that are well polished are very good reflector and bad absorber or radiators. And that's the reason why it's advisable to wear white clothes or brightly colored clothes in the sunny day, because they are good reflector of heat, whereas black clothes are good absorber. Please take note. Now, let's use this knowledge of heat transfer to explain its application in vacuum flask or thermoflask. Now, a vacuum flask is an apparatus which keeps a liquid stored in it in a relative constant temperature in a period of time. That means if I put a hot water or a cold water in this thermoflask, it remains fairly that same way. And this is due to interruption of this heat transfer mechanism. Now, for instance, we have a cork at the bottom, we have a vacuum sealed by two layers of silver colored or painted surfaces. We have an insulator stopper, then covered with a metal case. Now see, the stopper, which many times can be plastic or wood or even rubber, bad conductor of heat. So it hinders the loss of heat It hinders loss of heat via conduction, and also this heated fluid transmits heat to it via convection. So it also stops it via convection. So it prevents the loss of heat via conduction, because this is a bad conductor of heat, and also via convection from the heated fluid. Secondly, the double silver coated inner surface prevents heat loss by radiation. Remember, we said silver colored or white colored surfaces are bad radiator. So they don't allow heat to be lost through radiation. They are bad absorber. So the heat radiating from one part of this surface is hindered by the second part, because of it is silver coated, is silver painted. So it prevents heat loss by radiation, because they are good reflector of heat. Also, the vacuum prevents heat loss by convection. Remember that vacuum means fairly there are no air, and remember that convection needs air, needs fluid. So it prevents heat loss by convection. Now the cork at the down, which is also a poor conductor, prevents heat loss from this metal surface by conduction. So all of these mechanisms, all of these parts is what makes our vacuum flask to keep its contents in a fairly constant temperature over a period of time. Don't forget, the vacuum prevents heat loss by convection. Remember, fluid, air. There are no air in vacuum, apparently. The cork and the stopper, which are bad conductors, prevent heat loss by conduction, and the stopper also by convection from the heated fluid. And the double silver coated inner surface, which are good reflectors and bad radiators, prevent heat loss by radiation. Now let's advance to talk about the calculatory aspect of expansion. Now, before I delve deeper into expansivity, I want to explain a wonderful phenomenon that happens in water, which is known as the anomalous behavior of water. Now, water and few other liquids have an abnormally, let me call it that way, an anomalous behavior when heated. Let's say water at a temperature of, let's say, minus 15 degrees Celsius. As it is heated and reaches onto zero, we know that the ice begins to melt. Yes, at the same temperature, that's the latent heat of fusion. At the same temperature to become liquid. Now, between 0 degrees Celsius to 4 degrees Celsius, we know from the beginning of the class that heat causes expansion. So from 0 to 4, we should also expect an expansion. But water does something unique. Between 0 degrees Celsius to 4 degrees Celsius, water begins to contract. Then from 4 degrees Celsius and above, it continuously expands. That behavior of water at 4 degrees Celsius is known as the anomalous expansion of water. And that's the reason why you will see in polar regions, you will see the sea or lakes are already iced, whereas the deeper part of the water is still liquid and it gives way for aquatic life to still live. It's because when water is cooled below 4 degrees Celsius, it becomes lighter and then it goes up, forming ice at 0 degrees Celsius. Whereas the water below are still around 4 degrees Celsius. And that's the reason why the top part of these lakes are ice, whereas the bottom is still liquid. Because any temperature lower than that, water behaves abnormally and becomes lighter and then goes up to form ice. So that's the anomaly. So in any exam you come across where you are being asked, at what temperature does water behave abnormal? Is between 0 to 4, where it contracts and has its higher or highest density and least volume. Now let's talk about expansivity. Now, linear expansivity is the increase in length per unit length per degree rise in temperature. What it means in our formula side, our formula bank, linear expansivity is in this form, is equals to increase in length all over initial length multiplied by change in temperature. Now, the second one is area expansivity. The symbol is our beta sign. Area expansivity is actually 2 times of linear expansivity. Linear expansivity just has to do with length, whereas area expansivity, remember area is length times breadth, or length square is times 2. So area expansivity is times 2. That means area expansivity is change in area all over initial area multiplied by change in temperature. Thirdly, we have volume. You can also call it cubic expansivity. You know, volume is length, breadth, and height, 3 dimensions. So, volume is written in a symbol of gamma. So, volume expansivity is 3 times of linear expansivity, and also 2 of volume expansivity is equals to 3 area expansivity. 2 volume expansivity is equals to 3 area expansivity. So cubic expansivity is equals to change in volume all over initial volume times change in temperature. There is something of note also. When a liquid is heated in an expansible container, where not only the liquid expands, even the container itself expands. In that case, it brings us to what is called real cubic expansivity. Is equal to the apparent cubic expansivity plus the cubic expansivity of the container. Now, the apparent cubic expansivity is the increase in volume per unit volume per degree rise in temperature of the liquid when heated in an expansible container. Whereas real expansivity is defined as the increase in volume of the liquid per unit volume per degree rise in temperature. Now, it is always higher than the apparent expansivity because we always take into consideration also the expansion of the container. Now, apparent cubic expansivity can be calculated by knowing the volume or mass of liquid expelled all over the one remaining times temperature rise. So these are very important formulas in expansivity that will be seeing its application soon. So please take note. We have linear expansivity, that has to do with length. Area expansivity has to do with area. Cubic expansivity has to do with volume. All of them. So now this change in length means L2, the final length minus the initial length L1. The same thing with this, the same thing with this. So now can we go and use all of this knowledge and crush UTME questions? Come with me. In what range of temperature is water anomalous? We already know this. Water behaves anomalous between the range of 0 degrees Celsius to 4 degrees Celsius. That means our answer is E. So the next question. At 4 degrees Celsius, the volume of a fixed mass of water is, now this is also related to the anomalous behavior of water. Remember we said at temperature lower than this, let's say for instance -10, and we begin to heat water, it expands, which is normal to every liquid, to most liquids and solids. But when it reaches to 4, it's between 0 to 4, it begins to contract, and its contraction reduces volume. That means at 4 degrees Celsius, the volume is minimum, whereas the density is maximum. So the answer is minimum. To the next question. A blacksmith heated a metal whose cubic expansivity is 6.3 exponential -6. The real expansivity is. Please don't confuse this with the real expansivity of this. That's not what is meant here. Remember, real expansivity and apparent expansivity has to do with liquid, but our context here is a metal. So what this real expansivity means, it means the mean linear expansivity. Please take note, because real expansivity is for liquid alone. Now let's solve it. Now we know that by this formula, cubic expansivity is 3 times linear expansivity. So they said cubic expansivity is 6.3 times 10 to the power of -6. So divide both sides by 3, divide both sides by 3. Our linear expansivity will give us a 2.1 exponential -6. That means our answer is what? C. To the next question. Which of the following is not an application of expansion in metals? The metallic strip thermometer, temperature control in electric iron, compensated balance wheel of the watch, and sagging of telegraph wire. So remember, in our class, there is difference between the effect of expansion and the application of expansion. Effect many times can be undesirable, but the application is using the knowledge of expansion for something good. Now, the metallic strip thermometer, we said, is used as a thermometer, knowing the difference in the rate of expansion between the brass and the invar or steel. So it's correct. Temperature control in electric fan, use of the bimetallic strip. Correct. Compensated balance wheel of a watch. A watch during expansion, there is loss of time. So when there is a compensated balance wheel, it helps to avoid that loss of time. So it's also an application. But the sagging of telegraph wire is an effect of expansion. So it's undesired. So our answer is what? D. So the next question. A wire of length 100.0 meter at 30 degrees Celsius has a linear expansivity of 2 exponential 5. Calculate the length of the wire at a temperature of -10. Now the first thing is our culture in Josh White Academy is to first write the data. Now, a wire of length 100, that means the L1 is 100.0 meter at 30 degrees Celsius. That means our theta 1, our initial temperature is 30 degrees Celsius. has a linear expansivity. Our linear expansivity is 2 exponential 5 per Kelvin. Calculate the length of the wire. We have been asked to find L2, where the temperature is -10. That means our final temperature is -10 degrees Celsius. Having got out your data is now then easy. The next thing is to find the formula. Linear expansivity is this. Our linear expansivity is equals to change in length, which means L2 minus L1 all over initial length L1 multiplied by change in temperature, which means θ2 minus θ1 in an expanded form from that condensed form. Now, let's substitute our data. Our linear expansivity is 2 times 10 to the power of 5. Our L2 is what we are looking for. Our L1 is 100. Our L1 is 100 multiplied by our θ2 is -10 minus θ1 is 30. Please take note. Don't do the other way around. It will give you a different answer and you will find it in the option. So our θ2, which is our final temperature, is -10 and our initial temperature is 30. Now let's solve. -10 minus 30 is -40. And -40 times 100 will give you, that means you will have a 2 exponential -5 is equals to L2 minus 100 all over -40 times this will give you -4000. So cross multiply that L2 minus 100 is equals to 0.08 minus 0.08. And if we collect like terms, L2 will be equals to minus 0.08 plus 100 is as same as saying 100 minus 0.08. This will give us our final length of 99.92 meters. So our answer is what? D. Please always take note. So let's take the next question. The linear expansivity of brass is 2 exponential -5 per Celsius. If the volume of a piece of brass is 15.00 centimeters cubed at 0 degrees Celsius, what is the volume at 100 degrees Celsius? Our data. The linear expansivity of brass is 2 exponential -5 per Celsius. If the volume of the piece of brass, initial volume is 15 centimeters cubed at 0 degrees Celsius, and our initial temperature is 0 degrees Celsius. What is the volume? So we are finding our final volume, and our final temperature is 100 degrees Celsius. But now see, we are dealing with volume, but we are giving linear expansivity. Is to check if truly the student understands what he needs. We don't need linear expansivity actually in this question because we are giving volume, a 3D kind of calculation. So we need to convert the linear expansivity to cubic or volume expansivity. And how we do that is by multiplying it by 3. Remember, cubic expansivity is 3 times linear expansivity. That means our volume expansivity is 3 times 2 exponential -5, which will give us a 6 times 10 to the power of -5 per Celsius. So from here now, let's use our formula for volume expansivity. So our volume expansivity is equals to changes in volume, which is V2 minus V1 all over initial volume times change in temperature, which is θ2 minus θ1. Now, our cubic expansivity is 6 times 10 to the power of -5. Our final volume is what we are looking for, V2 minus our V1 is 15 all over Our initial temperature is also 15 times change in temperature is theta 2 minus theta 1. That's 100 minus 0. Now let's solve. Simplifying here, 100 minus 0 will give us 100. 100 times 15 will give us 1500. That means 6 exponential minus 5 is equals to V2 minus 15 divided by 1500. So let's cross multiply. This multiplied by this. So here will give us our V2 minus 15 is equals to 0.09. We collect like terms, V2 is equals to 0.09 plus 15, which will give us a 15.09 centimeter cube. That means our answer is 15.09 centimeter cube. Let's take the last question. During summer, the balance wheel of a clock expands. What does this have on the accuracy of the clock? A. The clock gains time. B. The accuracy is not affected. C. The clock loses time. And D. The clock stops working. Please take note. In the balance wheel of a clock, when there is expansion, the clock always loses time. And that's why the application of a compensation to stop this from happening. So in expansion, the clock loses time. So our answer is C. If you gained something from the video today, I know this video was lengthy, but if you gained something from the video today, please do well to subscribe if you've not subscribed before. Also do well to like the video. It's very important. Also comment and share. In the next class, we will be talking about the equilibrium of forces. You can't afford to miss that class. So I remain your host, Josh White, leaving to catch you another day. Peace I live with you.